Hey, welcome back. Good to see you again, and hope you're all well. Thanks for joining the channel. So look what I got at my bench today. This is a Citation 24 high voltage, high current power amplifier. So these things are beasts, apparently. You can see it's got a nice black aluminum faceplate with hard rubber. It's kind of the design of the day for the Citations. This is kind of rough here, chewed up. So this one came to me from a place far, far away through a website called eBay. I purchased this one about a year ago, and I got it for a good price too, I think. Anyways, I still paid a lot for it, but I think I still got it for a fairly good price, considering if I look today and see what they're going for. Yeah, I think I'm okay on that end of it. But it does have problems. It's got two problems that I know about so far. And let's plug it in here. We'll show you one problem. And we got 900 milliwatts of standby power. If we turn it on, if you can see this, consumes about 23 watts, and the protect light is on. So for whatever reason, it's in a protect mode. And I haven't hooked anything up to it to see if it's putting out a signal. I'm assuming it's not. So yeah, and it's not the greatest physical condition. It could use some cleaning, and it's a little scratched up and dinged here and there. But I'll turn it around and I'll show you something else. Alright, here's the back. Got our inputs, gold-plated inputs left and right, gold-plated ground screw. We have a switch here that can be locked in one position or the other, and this is the bridged mono switch. So it's right now it's off, so we're in stereo mode. If I were to flip the switch on, it would set up the amplifier for bridge mode. And we have our speaker operating modes for the left and right channel, and there's two switches, and they're both set up right now for 8 ohm loads, and we can adjust this for 4 ohm loads. This is common for a lot of Harman cards of this era. What they're doing is they're tapping into different secondary windings on the power transformer. Okay, and then we have our output. Now this is the problem that I discovered when this arrived. I think it might have taken a hit in shipping and got knocked in. This is pretty vulnerable, so we're gonna have to repair that as well. I think this is broken. Alright, so let's get the cover off, have a look inside. The big reveal, my camera doesn't go back any farther, so this is quite a big beast. It doesn't want to cooperate. There we go. Take a look at the inside of the lid. Everything looks good. A few dents, it's not a big deal. And here we go. And here it is. Citation 24. Now I'm kind of surprised this power transformer doesn't look all that big for what it's going to do. Right off the bat, I don't see anything outstanding here. Anything weird. What's going on with this thing? This thing's broken. See the two screws got pulled out. So it must have took a hit in shipping. I don't know if that happened when this came to me or if previous owner had this problem. It looks like somebody was in here because they had drawn a little an arrow, and they tried fixing it with welding it with their soldering iron. That's not going to hold. And there's a little bit of epoxy here. So this is a known thing. It probably happened to them when they bought it. Things are disconnected here. Yeah, the speaker outputs. So we have a little investigation work to do to figure out why this thing is in protect mode. And right now I don't see anything jumping out at me. Everything looks pretty good. This here looks like some kind of a driver board on this side. Okay. We got 4 fuses here, 6.3 amp, they're all intact. We have 1 transformer and we got 2 power supplies. So there's that 2 sets of bridge rectifiers, 2 sets of capacitors, 1 for each channel. This does not look factory, does it? What is going on here? Maybe it is factory. A lot of heat shrink on that. All right, I'll see if I can remove the bottom. Oh, I missed one. A little bit dusty, but I think somebody's been in here before. So let's put this aside. Let's have a look. I'm not seeing anything wrong here. Everything looks normal. Interesting. They have provisions for extra transistors here on the outputs. Everything looks factory here. I don't think anybody's done any soldering. I'll get my meter out and I'll check these output devices. I don't think there's any of them bad, but we'll soon see if that's the case and figure out why it's going into protect mode. Okay, just to start, I want to try measuring if we have any DC on the outputs. And this is our speaker outputs right here. This does not have a relay, a protect relay. It relies on electronics to protect it. So let's see what we have here on this channel. Turn that on. And I'll just wait. We got 10 millivolts right now. It's not changing. 13 millivolts on that channel. I went through and checked all the output devices. There's no shorts. Okay, so we should be okay. I don't know why. Let me see what voltages we have here on our capacitors. Where are they? Let's see here. This one here, minus 58. Minus 58. Okay. This one here is plus 58. Plus 58. So your voltages are there. Our devices aren't shorted. There's no DC on the speakers. 13 millivolts there. 11 there. I think it's probably something further back in the front of the amplifier. It doesn't seem like our outputs are the problem. Either we got a problem with the protect circuit or we got a problem with the circuit it's protecting. So there is a printed circuit board up here I don't know, I have to pull out the manual and figure out what this board does. Looks like it's mostly not populated, and there is some stuff there on the top. Okay, I know you can't see what's on the schematic here because it's pretty busy. But this whole circuit board down here, that is the protect board that is on the front of the unit. That's up here. There is a protect board, and I can see it's all populated with some parts. And that's the board that pretty much runs the display LEDs in the front. There's a circuit here that turns on this voltage overload. There's two LEDs here, and this is the protect light. I should write that in there. Okay. And then there's another LED display here for the high voltage, high current modes. And so this whole area is powered by these lines that go up here, and there's a little plus minus 12 volt voltage regulator, and I just want to check and make sure I got voltages here. That would be the first step, to make sure we have correct voltages, because if there's a voltage missing on this, that'll throw this off, and then it'll trigger that. Aside from that, this protect lamp here is turned on by this transistor, which goes back up to here and goes with this circuit here. This circuit here looks like the brains of the unit. We have two temperature sensors on this side, and that's biased with this transistor, and then this transistor. So if this goes over temp, this transistor turns on, and it will, let's see here, turn on the protect circuit. Now that's that half. This half, right from here, is a line. This side here has to do with DC offset. I'm pretty sure it's DC offset and overload of the amplifiers. This side's temperature, this side's monitoring the electrical of it. So we have a transistor here and here, which is monitoring the outputs of both channels, and that will turn this transistor on or off depending on its state, which goes back and triggers the protect. So after I check these voltages and make sure these are running, I'm going to go in here and I'm going to find Q6 and Q5. If either of these transistors are turned on, it's going to go into protect. Either a temperature overload or over temperature, or a DC balance condition, or something like that. We know we don't have a DC balance condition because we checked the outputs of both amplifiers and they are clear, because there is no switch between the output of the amplifier and the output of the speaker. Okay, it's just a solid wire. There's no speaker relay, there's no fuse, there's no disconnect, no switches. So it's a straight shot out. Okay, so we know we don't have a DC offset, but we want to see if maybe something's triggering this circuit. So let's first check this. Plus minus 12 volts, and I think it's up here. I have a couple capacitors and two transistors, and I think that's the circuit. Problem with this board is it is very difficult to read, because the silk screening on the top is pretty poor condition. It's hard, it's small font, and it's hard to read. Okay, can you see my meter? Okay, let's see this one here. We should have plus 12 volts. Here we should have 12 volts. Okay, so we got 12 volts on both of those. What is our input voltage? Let's see here. 12 there. 0, 0, 12. Okay, going into the collector, we've got 50 volts on that one. Negative 52 on that one. Okay. So that little power supply checks out. Okay, that's good. Now we need to figure out where Q6 and Q5 are, and then I need to check the signals on those two transistors. Okay, I found Q5 and Q6. They are hidden here. Both collectors and emitters are tied together on these two transistors, and just the bases are being fed by two different signals. So let's see what this says here. You can do this without shorting anything out. That is at 0. Do I have a good connection? 0 volts. That would be the emitter. Okay, that's grounded. Yeah, that's correct. Okay, the other collector is at 5.5 volts. And you can't see that because it fell over. That could be a bad sign. Let's see here. Something might be turning that transistor on. Let's check this one. So much flux on this board. Okay, this one shows 0. This one shows 0 as well. Okay, maybe that transistor's off. Something is not adding up here. Beginning to think we have a problem on the protect board. Because everything looks normal on here, everything's measuring normal so far, except this. Something's turning this protect LED on. Q116. Let me check this transistor too while I'm here. Q116 is the one that switches this LED. So, emitter. Emitter's grounded, yes. The collector should be 5.5 volts. And it's not. The base should be 0. And it's not. It's 0.7. Let's check Q117 as well while we're here. Emitter should be 0. It's grounded. Okay. The collector should be negative 0.1 volts, and it is negative 4.5 volts. The base should be negative 0.6. Hey, maybe that's our problem right here. Maybe this transistor's bad. This is reading 0. Something's turning this transistor on. Huh. Maybe we got a bad transistor there. Let's check this. I'm going to pull this board out and investigate this further. Okay, so I finished going through these two boards. This is the display board here, and this one is the protect board. I did find a bad cap on here. This is a 33 microfarad at 16 volts, and it tested out at 7 microfarads, and it had a really high ESR. So it was failing. It was going open, and that capacitor is right here. What is this called? C108, and it's 33 at 16. Now this is the over voltage circuit. So this is not our problem. This probably wasn't a problem for that either, but you know, a bad cap, so I changed it. It's all done. So this is all gone through. I haven't tested the op amp, but everything else in here is working and tests fine. All right, I think I'm starting to make some headway here. What I did is I removed the pre-driver board. This is the amplifier section that has all the input section, the long tail pairs, and the voltage amplifier section. And then it goes on to the main board where it goes to the output devices. So I pulled this board out because there's a lot of it I couldn't access. It was hidden behind plate of steel here, and I couldn't access probably the bottom third of the board. So I pull it out, and to my surprise, got cracked solders, cracked solders, cracked solders, and cracked solders. And I think I found our cause for the malfunction. There's one resistor here that's completely broken away from the pad, from the crack, and this resistor is R525. So what does R525 do? Let me show you. So R525 is right here. It's a 1.2K, and this is on the positive supply rail, and this is the negative supply rail down here. So what this is a dropping resistor, and then there's a zener here, and what they're doing here is they're regulating everything to the left of that resistor for these transistors here. See, this is the same thing here. They got a 1.2K zener, a pair of zeners actually, and this whole section here is regulated by these zeners, the power supply. R525 was broken connection, so this portion of the circuit was not being fed voltage. So that would be enough to upset the balance, trip a protect, and prevent this amplifier from working. So I'm going to go through and solder all these connections back up. These transistors down here, they have cracks on them too. Not as severe, but there's still some cracks. And this area here is soaked with heat. This area is here soaked with heat. So I'm going to be checking all these capacitors as well. I don't expect all of them will be bad, but I expect to find a few bad ones, and I'll replace those and get those soldered back up, and hopefully we get this amplifier back on the road again. Alright, so I finished reworking this pre-driver board, and I'm kind of happy with the results. A lot of different crack solders all over the place in this area, especially in these corners where there's a lot of heat with those zener diodes and those dropping resistors. I replaced 6 capacitors on this board, and I'll talk more about the capacitors later, what I found. These were all defective, so I replaced them and cleaned up the flux. So I had a good inspection with a magnifying lens, make sure I had no solder bridges. Everything looks good. Time to put this board back in and see if this amplifier is going to work now. I have a feeling it will. This here was reworked. This one had this is the input, and then I think this is a phase inverter for the bridge mode stereo switch. And I did find some bad caps on here as well. I replaced those. That's going back in. This here is the standby power supply. Everything's good on this. I'm going to clean this board and then put everything back together, and we can have a test. Okay, I got everything back together again. I resoldered this board and reinstalled it. I went through and resoldered the main board. There's a lot of areas here on this right hand side where there's transistors on heat sinks and stuff. You're probably going to find cracked solders as well. So go through and I resoldered the main board as well. Majority of it didn't need it, but like I said, on this right hand side there's a lot of flaky looking solder joints. So I went through and did that. Capacitors, well, I did change a bunch of capacitors. You can see here. These blue ones, I don't know if you can see them, but they're all starting to leak. Big in focus. There we go. You see how they're starting to leak? And these are these blue Mashita or whatever they're called. Panasonic ones. I just yanked all the blue ones out and replaced them, even in the good ones. And there was a few other ones here. This is another one. These ones are bigger, but they're purple. These are 2200 at 6.3 volts. These measure down around 1400 microfarads, so they got replaced. Not too many TK caps because I was impressed. TK caps are holding out today. These are the TK ones, and these were in the preamplifier, or these ones were in the power supply circuit, and they were getting weak, so they got replaced. Let's plug this thing in and try it out. We have power is off. Okay. If you can see that, I think you can. Okay, so we're drawing again 0.9 watts. There's a little transformer there that's doing standby work. I don't understand why it needs a standby. There's no remote. So let's turn this on. And it came out of protect. Green light on, so we're online. So it looks like we're fixed. It's drawing 80 watts and climbing. Hallelujah. So what we're going to do now is we are going to set up the amplifier. We have two adjustments. We have DC balance and we have idling current. So I'll get through those. I'll set up the camera and we'll do that together, I guess. This looks like an involved process. Connect 100 ohm resistors shown in the figure. Okay, we'll get to this. So we have a working amplifier now. That's good. That's nice. All right, so here we are. Here's our instructions for the DC balance. Set the speaker operating mode switch for both left and right channels to the 4 ohm position. Okay, I've done that. Allow 20 minutes of warm up. Okay, done that as well. Connect the digital voltmeter to the speaker terminal and adjust VR401 for the left channel and VR402 for the right channel, so that we have 0 millivolts DC on the voltmeter. And then we go to 8 ohm position. Allow 10 more minutes for it to temperature compensate, and then we check it again, make sure it's plus minus 60 millivolts. Okay, so right now I've got a voltmeter here. It's showing 6 millivolts, 6 or 7. It's kind of jumping around a bit. And I'm doing the right channel, so the right channel is V402. It's right here. Don't really need to adjust it, but I can. I'll show you. We can zero this out. Wow, it's very touchy. See if we can get this close again. Should have just left it alone. Minus 15. Okay, I'm going to leave it at that. Now I'm going to switch my probes to the left channel. So let's do that now. And here we have negative 68. Okay, so our adjustment point is over here on the right hand side. This is left channel. Let's turn this. So we can get a balance right about here, right there. Okay. That should be it. Now, I'll switch this over to 8 ohms. I'll click the switches now with it powered up. And it's switched. Seems to be climbing. Let me check the other channel. Okay. Okay, I'll give this 10 minutes and I'll check that. If it's within 60, I'm just going to leave it alone. I got my 400 ohm resistors here, and they are 5% tolerance, but I checked all these. They're within 1%. So, good enough. Let's see here. Let's just tack these together. Find my solder. Okay, let's just tack these together temporary, because I'm going to just take it all apart when I'm done anyway. There's our center points. That's where we take our measurements from. And then I'm just going to use 2 clip leads. I'm going to sacrifice 2 clip leads, cut them in half, strip them, and then we can use this as our attachment to the board. Okay, take our yellows. I'll just solder these together. I'll do the same for the other one. So we got our center point, that's where we attach our voltmeter. And these 2 clips go to the main board. So we're going to have to figure out a way to keep this from shorting. Maybe I'll just wrap it with some tape or something. Just, it's this all temporary rig here, so we can just do our measurements, and then when I'm done, I'll take it all apart. Okay, so since we have 2 sets of outputs, we have 2 sets of emitter resistors. See, here's one set of transistors, here's the other set. Emitter resistors in the middle. So how do we adjust the current through this leg and this leg? Well, we don't. We take an average of the both. So that's what they're doing here. From this emitter, this line comes out to here, and where's the other one? This is odd. So we have resistors coming out here and here. This is 100 ohm here, 100 ohm here. And then we have 100 ohm going down here. I thought it would be connected here though, not at the base. That's odd. I find that a mistake in the schematic. I bet you that's not correct. Anyways, what we're doing is we're connecting resistors across these 2 terminals and these 2 terminals, and then we're taking an average of the 2. We're measuring across here, so we're going to measure the average between this and this, which is what we're doing here. We have 2 sets of terminals here, 2 sets of terminals here. We put our rig on and we measure the average between all these. And what we want is we want to adjust it to 32 millivolts plus or minus 3. So let me get this all connected and warmed up, and then we'll come back and we'll do this adjustment. Okay, one thing that's confusing me right now is these instructions for the idling current adjustment. Sorry, right up here. There's no mention whether this should be in the 4 ohm mode or 8 ohm mode, because there is a difference when we switch it around. Now I think if you're doing this for yourself, this is your amplifier, you know your amplifier, you know what kind of speakers you're going to be running on it. If you plan on running 8 ohm speakers, I would set it up in the 8 ohm mode. And if you plan on running 4 ohm speakers, I would set the bias current with in the 4 ohm position. But right now I got it in 4 ohms, and you can see we're drawing 59.5 watts idling, and we have 49 millivolts. So if I switch it to 8 ohms, watch what happens. See how it jumps up? And we are now drawing nearly 80 watts. Well, we are 80 watts at now. So let's do this in the 8 ohm mode, because I typically run 8 ohm speakers. And so this is warmed up now. I got my rig connected with my four 400 ohm resistors. So let's tweak the bias here, and let's see if we can turn this down. It shouldn't be that high. It should be 33 or 32. I can't remember. We'll put it at 32 and a half. What does it say here? Yeah, it's 32 plus or minus 3 millivolts. So that's going to go down a bit because it's going to cool off now. And what I'll do is I'll just wait for this to stabilize, and I'll tweak it again to make sure, and then we'll move on to the other channel. Instead of swapping leads back and forth, I'll just do one channel complete and then finish it. And what's our consumption gone down to now? It went from 80, we dropped almost 10 watts down to 69.5. Okay, here we are connected to the left channel now, and we can see we're still at 69.3 watts. So let's adjust the left channel. I'm going to turn this one down as well. These amps should run a lot cooler now that we turned down the bias. That's pretty good there. Now we're down below 60 watts, which is more reasonable than 80. I'm just going to let this temperature compensate and balance, and if it doesn't drift, I'm just going to call it done and leave it alone. Alright, now that we have a working amplifier, we have to figure out a solution for our speaker terminals. So I removed the board, and here's what I found. Somebody had this apart, and they got a little happy with the JB weld, which is fine. I don't mind this, because it came, looks like it came apart into 3 pieces. It's got a big crack this way, so this lug broke off, and then this one's cracked here, so this lug broke off. These 2 are still intact, so they welded them all back together with this JB weld. And it seems fairly rigid. I'm not, I put some force on it. It doesn't want to break apart. But we have to figure out how to mount this to the back panel. And look, somebody, the screws pulled through, and I found a whole bunch of little shards of pieces of black plastic when I took the thing apart. And that explains where they came from. So the only thing holding this on is 2 screws. You can see here and here. And I don't trust those screws to hold anymore, because there's pieces that look like are ready to flake off here. So what do we got to do? We have to, this mounts on here. Okay, push that. There. So that goes on there like that. What I was thinking of doing is taking a drill and drilling these 2 holes out, probably 3 millimeters, and I'll drill them straight through the PCB board as well. We've got 2 holes here. This is fine because these 2 conductors are ground potential for the speakers, right? These 2 are live. So if I drill a hole through, I should be able to put it on here and put a screw with a nut on the end and hold the whole assembly in place. I'll have to provide an insulating sheet here, and then I was thinking maybe a steel plate behind it to back it up so that we're not putting any undue force on this printed circuit board. It's not fiberglass. It can snap. I don't want to break that. But if we have a screw and it clamps everything tight, it should hold it all together. You got your back panel here. You got your speaker connector, your PCB board, insulating sheet, and a steel plate. And if they're all sandwiched together and tightened up with a screw, it should all hold together and it shouldn't come apart ever again. I think that's what I'm going to do. So what I'll do is I'll drill these two out. I'll measure the distance between them. Actually, I'll drill out this PCB board so that I have some clearance so that it won't short and touch the screw, because then we'll get a ground loop. I'll make this hole bigger here so it provides insulation. I get an insulating sheet, a steel plate with 2 holes in it. I'll find some machine screws, probably going to need to be about 20 millimeters long or so, and we'll put it all back together and see how it works. Alright, so I think I got everything prepared here. I took the printed circuit board, and what I did is I matched the holes, the two mounting holes, drilled through the PCB board, the right location, and then I chamfered the holes to cut back the copper foil so that they can't make any contacts, so that like when the screw comes through, there's no chance it can short. So I got that. I cut an insulating sheet, a little long, I can trim it after. And I also cut this steel plate. This is a little out of sheet metal. Actually, I think I got this a little long too. No, it's good. So that's going to provide clamping from the back so that we're not putting all the pressure on the PCB board. And we've got these 2 holes drilled through so that we can now pretty much assemble everything. I think we're ready. First step would be solder this back on. The red to the top. So let's solder these connections so that we can put everything back together. If my iron would warm up. So make sure that is bottomed out. A lot of heat when you got a big copper foil. All right, now we got that. We should be able to assemble this. A lot of people don't like these connectors because Harman Kardon, in their owner's manual, what they do is they specify that you take the end out and you feed the wire through the hole, and then you fan the strands of the wire over this gold ring and then screw it back in. It's kind of a pain, but they don't really tell you that there's a hole in the side you could feed a wire through and then clamp down. So that's, I bet you a lot of people didn't know that. Okay, let's push this in place. Looks like it's bottomed out. Okay. Now I'm just hoping I got the screws long enough. This one's 20 millimeters. Yeah, 20 millimeters. I got longer ones here, but they're different thread. So let's see if this one works. Feed this one through. I'd have to. That's going to work. Insulating sheet. trim that. And metal plate. Let me trim the sheet right now because it is in the way. Okay, metal plate. We've got just enough room for a nut. Okay. Let's try the other screw. The other screw's longer. Probably going to end up cutting it so that they're both the same length. Hang on a sec here. Okay. And I hope I drilled my holes correctly. Okay. I got some fine tuning to do here. I think I got my plate on upside down because it's hitting on the heatsink here. So I'm going to take my plate out, flip it around. I'm going to trim this insulating sheet down, and we'll button it up. Just give me a sec here. Alright, there it is. I put some thread locker on these nuts so they don't come loose, hopefully. Yeah, I think I might have to. Since I tightened those nuts down, this board is a little warped, so I'm just going to reflow these joints. Now, it's solid. It's not going anywhere. It won't take a hit in shipping like it did before. It would probably break it again, but at least it's solid and it's not. You can attach wires to it. It's not going to fall apart. It's clamped very, very nicely and tight. I don't think there's anything more I can do for this. I know it doesn't look great. A little bit crooked on my sheet metal and whatnot, but I think it's an effective fix. From the outside, it looks very, very normal. It's just got two screw heads, which would be there originally. So yeah, I think we're good. Okay, so let's move on to power tests. I think we're all done with repairs. All right, let's do a power test on this thing. I'm curious as what it can do. Specification wise, it got a little different. Well, not really different. The service manual says we should be able to get on 8 ohm load at 1 kilohertz at 0.08% distortion. We should get 111 watts. And out of 4 ohm load we should get 114 watts. The owner's manual, however, has different specifications. It says continuous average power at 8 ohms is 100 watts per channel. Both channels driven from 20 hertz to 20 kilohertz at 0.08 THD. 4 ohms, 100 watts per channel, 20 kilohertz, 0.08 THD. And 8 ohms bridge mode, we should get 200 watts. But they have down here some other ratings. These are tone bursts, 1 kilohertz tone burst, 1 channel driven. 8 ohms, 140, 4 ohms, 210, 2 ohms, 325. That's in the high voltage mode. High current mode, 4 ohms is 140, 2 ohms is 210, and then in bridge mode we get 8 ohms, 280, 4 ohms we should see 420 watts. I'm not going to check all of those out, but we'll do at least one 8 ohm, one 4 ohm comparison. Just switch this beast on and see what it does. Bring it out of a slumber and wait for it to wake up. Okay, there we go. Now we got everything live. I got my signal generator here is going to be doing the volume control work. So we can turn this up. And I got the wrong speed here, hang on. Okay, we want this, yes. Alright, so let's slowly turn this up. Okay, we're already into clipping. Let me turn this back down and adjust my scope. Okay. Let's go back up to clipping again. Right there, back it off. Squeeze these in. Okay, so we're at peak right now, and we are pushing 30.19 volts RMS. And we're drawing 399.5 watts from the outlet. It's doing this business right now. It's not even getting warm. Oh yeah, that's warm. Okay, I don't want to leave this too long because I'll cook my my load. Let's see here. That's clipping, yes. Yeah, that's a lot of power for this, my little load. I'm not gonna take it that far for that long. Let's turn this down, let it cool off. Okay, while we're on 8 ohm load here, let's do a square wave test. 1000 kilohertz. So here we go, we're gonna go back up. I'm at 13.75 volts right now in the output. So let's play around with the frequency here. 1 kilohertz looks pretty good. Let's go look at higher ones. 10 kilohertz. 10 kilohertz looks pretty damn good. Let's keep going. 15 kilohertz. Starting to see the fall times. The rise times look good, but the fall times aren't. Okay, let's go back up to 20 kilohertz. $25 kilohertz. Still looking good. $40 kilohertz. It's a pretty good amplifier to have a square wave at 40 kilohertz. Here's 50 kilohertz. Starting to see a little degradation on the rise and fall, but that's pretty damn good for 50 kilohertz. You don't get any better than that. Let's turn this down. We don't need to cook that. The amplifier has a power bandwidth rated at half power from 10 Hertz to 100 kilohertz. But it also has a frequency response of 0.07 Hertz, which is basically just DC. And it goes up to 490 kilohertz, which is AM broadcast territory. You can use this for a pirate station. But pretty impressive. Just doing that little bit of testing, it hasn't even warmed up yet. Okay, so we're all set up for 4 ohm loads now. The amplifier is set up for 4 ohms. I have my 2 4 ohm resistors. These are 100 watts each. And we are going to see how warm these get. I should move all these wires away, they might get cooked. And let's see what this can do. Okay, start putting the signal in. Turning up the volume. Okay. Let's see what we can do here. And I gotta readjust my scope again. Okay, let's take it up. Right there. Somewhere right there, I think is, and we are pushing 20.97 volts into a 4 ohm load. We're consuming 437 watts. And now they're starting to get warm. And yeah, these are hot. I'll let this go for a while. Actually, still into clipping. Right there, I think. Yeah, that's going to heat up a little faster. $430 watts here. We get how many watts coming out each resistor, and the rest of it is wasted as heat within the amplifier itself. Okay, I'm going to turn that down. It's pretty hot. Ooh, I can smell something warm. It's my resistors. Well, that worked pretty good. I don't want to touch these though. They're okay. One more test and then we'll be done. Okay, last test of the day. We got it in bridge mode, 8 ohms. I got it on an 8 ohm load. Let's see what this can do in 8 ohms in a mono. Oh wow, right there. We've got 53.47 volts RMS peak. And this thing's humming, and we're drawing 670 watts from the outlet. And my 2 resistors are starting to stink up the room, so I'm not going to run this for very long. It's a very capable amplifier, very powerful, very good specifications. If you pick up one of these, go through and repair it, do what it needs, but I'm sure you'll be pleased with the performance of this amplifier. It's pretty good. It doesn't have much for looks, but it's got the beans. So this is the parts I put into it. There's a little small handful of capacitors. These tested mostly bad, or I replaced them in pairs, so one might be bad, one might be good. Quite a few of these blue Mashita capacitors, wish I could learn to pronounce that name, are leaking. They have green corrosion around the legs. You can see it. Yeah, I think they're just tired capacitors. There is some heat zones in here that are cooking capacitors, and that's pretty typical of any amplifier. So you just got to go through and replace the bad ones. I didn't replace all of them, but I replaced probably, 15 of them here? 15, 20. Well, here it is. It's done. Citation 24. It's a very capable amplifier, like I said before, and I think the power tests speak for itself. And it's pretty much, this amplifier can pretty much handle anything. Very desirable unit. I'm not keen on the looks, the plain black box look, but what's inside is like magic. So it's a nice unit. Anyways, that's it for this one. I'm gonna enjoy listening to it, and gonna wrap it up there. So thanks for joining, and hope to see you on the next one. Take care.